Okay, the next example, example 7 in our lesson to complete section 11.1, is to find the limit as x approaches 3 of x squared minus x minus 1, and that is divided by the square root of x plus 1. So our function we have the limit as x approaches the value 3 of this rational function, and the fact that it's rational is very important because there is a potential that we could divide by 0 depending upon what x is. And in addition to it being rational, we have a radical in the denominator, so we also have to be very careful that the quantity x plus 1 is greater than 0. It has to be equal. It actually can't even be equal to. It has to be greater than 0. Because if it were equal to 0, we would have an expression that's undefined. So the issues we're going to run across is when x, as long as x is greater than -1, we're fine. If x is -1, we're taking the square root of 0. And if it were -1 or less, then we have the problem of it becoming negative. Fortunately, that isn't going to be a problem, though, because the number we're trying to approach is 3. So the way that we're going to do this is, first of all, we're going to take the limit of the numerator and denominator, with the numerator being x squared minus x minus 1. And the denominator being the limit as x approaches 3 of the square root of x plus 1. And we will take the quotient of those two limits. The limit of a quotient is the quotient of the two limits. So then the limit as x approaches 3 for x squared minus x minus 1, we can actually plug in the value 3. And 9 minus 3 minus 1 is positive 5. And then we can also plug in 3 for the bottom function. And the square root of 3 plus 1 is the square root of 4, which is 2. We're going to assume it's the positive root, because otherwise it's not a function. So the quotient of the two limits is 5 over 2. Therefore, the limit as x approaches 3 is actually going to be, for this function, x squared minus x minus 1 over the square root of x plus 1. That limit is actually going to be 5 over 2. Now we could break that down further, as a matter of fact, because this is the rule that says that the limit of a quotient is the quotient of limits. But what we're actually doing with the numerator here, there's a rule which, you know, this rule, it should be fairly obvious, but let's not assume anything. The way that we actually take this is, one of those rules says that the limit as x approaches some number of a polynomial function is equal to the limit of each term in the function. And I'm sorry, that's not cubed, that's squared. So the limit of x squared minus the limit as x approaches 3 of x, and minus the limit as x approaches 3 of 1. Of course, you know, 1 is 1 is 1 is 1 forever, so it doesn't make any difference. This limit is going to be 3 squared. The second limit is going to be 3, and the third limit is going to be 1, because regardless of what x is, that last term is a constant. And that's how we actually came up with 9 minus 3 minus 1, which gave us the positive 5. So these rules are actually rules that are intuitive, I think is the best word for that. They are intuitive rules. That it just makes sense if you need to take limits, that you could break it up and take the limit of each term. You can take the limit of a numerator and denominator. You can take the limit of a product by taking the product or taking the limit of each factor and then multiplying those two limits together to get the limit of their product. So example 11, we're actually talking about an applications problem where limits are used, and it says that we have a small pond normally contains 12 units of dissolved oxygen. And it's in a fixed volume of water. So at time t equals 0, we have a quantity of organic waste entered into the pond, and the oxygen concentration at t equals 0 is given by f of t is equal to 12t squared minus 15t plus 12 over t squared plus 1. Now, we don't necessarily know where this formula comes from, but we do know that it was derived probably using data observing this process happen in other situations. So what we've got is we've got a pond. And at some point, somebody has come along and dumped waste into it. And this is happening at time t equals 0, which means at the initial point of this. And then we have this formula f of t is equal to 12t squared minus 15t plus 12 over t squared plus 1. And it asks us, as time goes on, in other words, as t approaches infinity, okay, so what we're doing here is we're letting t approach infinity because we want time to move on. And since this is a situation in nature, then time will continue pretty much infinitely. So we're going to let t approach infinity of this function. And this function is f of t. Well, we can employ our rules for limits this way. We can take the limit as t approaches infinity of the numerator. And we can also look at the limit as t approaches infinity of the denominator, since that's what we've been doing. But the situation here is that if we do this, we're just basically saying what happens if t gets bigger and bigger and bigger and bigger. Well, if you square a large number, it becomes a function of itself larger, and then multiply that by 12, it gets really large really fast. So really the main influence is on the first term, and the same thing down here. So plugging in infinity directly really isn't a possibility with this kind of function. So what we're going to do is we're going to employ a little mathematical trick to make this something we actually can try to use infinity for. So the trick's going to work like this. We're going to take the limit as t approaches infinity of this expression. But here's what we're going to do with the expression. We're going to take the highest power of t in the denominator, and that's t squared. And we're going to divide every single term in this polynomial by t squared. And we can do that because basically we're dividing this by t squared over t squared, or multiplying it by t squared over t, well, no, not multiplying, but dividing both numerator and denominator by the same thing, which is legal as long as we do every term. And then we're going to try to take the limit as t approaches infinity of the simpler function. Although it won't necessarily look, I think, what we would call simpler in the beginning. So this is an equivalent expression. We're going to take the limit as t approaches infinity, or in other words, gets bigger and bigger. T squared actually cancels out here. So that's going to leave us with just 12. T is going to take away one of the t's in the bottom, so that's going to be minus 15 over t. And then that's going to be 12 over t squared. And then t squared over t squared is 1. And 1 over t squared is, of course, still 1 over t squared. And it's going to seem like I'm trying to be obtusely obvious here, but I have a reason for this. This function simplifies also to 12 minus the number 15 times 1 over t plus 12 times 1 over t squared over 1 minus 1 over t squared. Now for the moment we're going to leave off with that, and we're going to talk about what happens to 1 over t as t gets larger and larger and larger. So in order to do that, I'm going to get the calculator, and we're going to go into the function window, and I'm going to clear off what's there, and I'm going to enter in the expression 1 divided by x. And then, just as we've done before, I'm going to go to table set and make sure my table is set to let me ask for x values. So then we're going to go to the table, and we can think of a large number, but what we're looking for here is a pattern. So we're going to start out with 10 and see that 1 over 10 becomes 1/10, which should make sense. So then if we go to 100, we see that that becomes 1 over 100. And when we go to 1,000, that becomes 0.001 or 1/1000th. And I'm going to go to 10,000ths. And now we've switched to scientific notation in the second column because it can't show you all the digits. So I'm just going to continue adding zeros. Now, I hope you agree with me that as I have entered larger and larger numbers in x, I am in fact letting x, or t, approach infinity. And what's happening to 1 over x as x gets infinitely larger or increases without bound is that 1 over x becomes increasingly small. Not negative, but small. And in fact, the nearest rounding we're going to get eventually, and I'm going to actually try to put in some even bigger numbers. I think you're going to agree with me that 1 followed by 18 zeros is pretty darn small. And at this point, it says it can't even do that. It can't take e and raise it times 10 to the 100th power. It's beyond its limitations. I might be able to get it to do 99. Let's see. Yeah, it just says that that's a decimal with 98 zeros before you get to 1. So hopefully if you look at that, you say, well, okay, 1 followed by 99 zeros. If it's 1 over 1 followed by 99 zeros, that becomes the number 0.99 or 98 zeros, and then 1. And that is so close to 0, it's ridiculous. So now let's investigate, and hopefully this makes sense to you also. Just as 1 over x can be allowed to approach infinity, we can do 1 over x squared. So if I start out at 10, 100, 1,000, 1,000,000, a billion, and regardless of how high I go, it's going to get just closer and closer and closer to 0. And in fact, when I get so close to the limits of its information, it gives me an error message. It can't even tell me because it doesn't know how to interpret that because it's so close to 0. So here's the idea that we're trying to come up with, or here's the idea that I'm getting at. When you build this table, and I'm not building it for the whole function, when you build this table, we're talking about the limits at infinity for a number. And for any positive real number, as x approaches infinity, x to the nth power is going to approach 0. And even if we let x approach negative infinity, it's going to also approach 0, just from the negative direction. So given that information, if we take the limit as t approaches infinity, and working strictly on the numerator to begin with, of 12 minus the limit as t approaches infinity of 15 times 1 over t minus the limit as t approaches infinity of 12 times 1 over t squared, all divided by the limit as t approaches infinity of 1 minus the limit as t approaches infinity of 1 over t squared. This is what happens. The limit as t approaches infinity of 1 over t is 0. And 15 times 0 is still 0. The limit as t approaches infinity of 1 over t squared is also 0. And the limit of 12 times 0 is still going to give us 0. The limit as t approaches infinity of 12, well, there's no t here to approach infinity. It's going to be 12. The value of the function is going to be 12 no matter what t is. So that's going to be 12 minus 0 minus 0. And similarly in the denominator, the limit as t approaches infinity of 1. Doesn't matter what t is, that's going to remain 1. Minus the limit as t approaches infinity of 1 over t squared is 0. So 12 minus 0 is still 12. And 1 minus 0 minus 0, or excuse me, 1 minus 0 is still 1. So the limit as t approaches infinity is 12. Now, mathematically, what that tells us is that if we let t approach infinity, eventually the pond will return to having 12 grams of oxygen, or 12 units of oxygen. Realistically, that's going to take a lot more time than you would even imagine. So I'm going to go back and look at the previous slide. So this is what actually happens. When you start out, you started at 12 and the waste is dumped in. T is being measured in weeks. So within the first week, the oxygen level drops to somewhere between 4 and 5 units. And then over the course of the next week, it increases back to about 6 units. And then in a couple more weeks, it increases to a little better than 8 units. And by the end of 12 weeks, we're right at 10 and a half units of oxygen. Okay? But to think about how long it's going to take for it to get to that 12, if you let t equal 100,000, and let's see, I need some parentheses here. So there's 10 weeks, 100 weeks, 1,000 weeks, 10,000 weeks, 100,000 weeks, 1,000,000 weeks. And there's 1,000,000,000 weeks. Now you say, okay, well after 10,000 weeks it comes to 12. Well, actually no, it doesn't. It comes to 11.99985. And if you let it go to 1,000,000 weeks, it's 11.999985. And if you let it go 1,000,000,000 weeks, you are really, really close to 12, but still mathematically that is still not 12, and it doesn't matter how many zeros that I add, it never actually returns in reality to 12 units of dissolved oxygen. Now if you want to say you're close enough when you have reached 11.9985, well, how many years is 10,000 weeks? That's 192 years and a few months. So it will be a very, very, very long time, almost 2 centuries, before you're what most people would consider close enough. Even if you're talking about it being close enough at 1,000 weeks. It still takes over 20 years. And that's still, as you can see, not really back to 12 units. So this kind of limit is actually something that is used realistically in environmental science quite a bit, and in environmental businesses. So something to think about. So A couple more examples just to make sure that you have the technique. We're going to find the limit as x approaches infinity of the rational function 8x plus 6 over 3x minus 1. And the procedure for doing this is you first take your 8x plus 6 and your 3x minus 1, divide by the highest power of x in the denominator. So then you get the limit as x approaches infinity of 8x over x plus 6 times 1 over x, to make it obvious that this limit is going to be 0, over 3x over x minus 1 times 1 over x, because dividing by x is the same as multiplying by 1 over x. So what happens here, once again, is that the limit of this term as x approaches infinity, it goes to 0. The limit of this term as x approaches infinity, it also becomes 0. Since the x's cancel out in the first two terms, then what we're left with is 8 over 3. So that's the limit as x approaches infinity of the rational expression that we started with. Don't assume that it's always going to be the coefficient of the first term in both. It depends on what the highest power of x is in the denominator. Another example. We're going to take the limit as x approaches infinity or grows without bound of the expression 3x plus 2 over 4x to the third minus 1. And we're going to use the same technique. X cubed is the highest power in the denominator, so we're going to take 3x divided by x cubed. We're going to take plus 2 and divide it by x cubed. We're going to take 4x cubed and divide it by x cubed. And we're going to take, I'm sorry, that's supposed to be minus, not that it's going to matter, 1 over x cubed. So what happens here is x takes away one of those and leaves us with x squared in the denominator. And x cubed cancels out in the first term in the denominator. So now we take the limit as x approaches infinity of 3 plus 2 times 1 over x cubed. And 4 minus 1 over x cubed. And remember the 3, we still actually had x squared in the bottom, so we're going to go 1 over x squared. Because the x with 3 actually only wiped out one of those x's and left us with x squared. Well, the limit as x approaches infinity of x squared is 0, and 3 times 0 is in fact 0. And the limit of 1 over x cubed as x approaches infinity is also 0, and 2 times 0 is still 0. So that means our entire numerator is going to be 0. And at this point we know it really doesn't matter what happens on the bottom unless everything becomes 0. Then we have a problem. But right now 4 as x approaches infinity is going to remain 4. And 1 over x to the third, that's going to approach 0. So that's going to be 4 minus 0. This is going to be 0 divided by 4, and that means our limit of the original expression is then 0. As x approaches infinity, the value of that function approaches 0. Now, part C is a little bit different situation. In part C, we have the limit as x approaches infinity of the rational expression 3x squared plus 2 over 4x minus 3. So again, we're going to take the highest power of x in the denominator, which is x to the first, 3x squared over x plus 2 over x divided by 4x over x minus 3 over x, which is equivalent to 3 plus 2 times 1 over x. And 4x over x is 4. I'm sorry, this 3x squared over x is 3x. Sorry about that. Over 4 minus 3 times 1 over x. So what we have then is the limit as x approaches infinity of 3x plus 2 times 1 over x divided by 4 minus 3 times 1 over x. And what we see here is that the two terms that are multiplying times 1 over x, those become 0 and basically just disappear. But now we have a different situation from what we did before, because we're talking about the limit as x approaches infinity of 3x. And that limit is going to be infinity. As x increases without bound, it just also increases, the 3x increases by a factor of 3. The limit as x approaches infinity of 4 simply approaches 4, but infinity over 4 is still infinity. So what happens is x increases without bound. This function also increases without bound. So this is a summary of the process for finding limits at infinity. And that actually concludes our Chapter 11, Section 1 lesson. You should go ahead and do the homework for 11.1 at this point.